Hi, everyone. I think we have a very packed schedule for this session, so maybe we can get started. Good morning. It's good to see you. Good morning. It's good to see you too. All right. Welcome to the Introduction to Rubin session. This session is chaired by myself, Christina Williams, and Shenming Fu. We're both members of the community science team, the Rubin community science team, and we're going to hear a number of presentations from representatives from a variety of teams within the Rubin project to hear about what's going on in these different branches of the project. So we're going to go by a really, actually, how do you advance slides? Here, okay. All right, so I'm just going to give a brief introduction and then I'm going to hand this off to our variety of speakers that we have on the agenda. This is our agenda for the session. So we have a number of speakers. We are going to hand over the mic to these different speakers very quickly. So we're asking to please, if you have questions, definitely post those in the Slack channel. So we have a Slack channel here that's listed and you can post your questions there. And so since our agenda is very tight, hopefully we can continue the discussion online to make sure we stay on time. Okay, so just some quick reminders about the RCW. So we have a code of conduct, and so you heard about this in the last session, but we're hoping that everybody can engage in a professional and happy way. And so if you experience any issues with the code of conduct, you can contact some of these code of conduct contacts that are listed here, Sandrine Fed or Jeff Carlin. We also have, please keep in mind everyone's social batteries. If you are trying to engage with someone that has a social battery sticker on their badge, please be considerate of people's social batteries and also people's comfort levels for COVID-19. And so we also point out this lost and found. If you need to, if you lose something, you can go to the RCW registration desk. All right, so some reminders. If you're on Zoom, please keep muted and you can raise your hand, but also we're encouraging people to leave their questions in the Slack channel for this session so that we can keep on time with this session. All right, and so again, welcome to the Rubin Community Workshop. We have a number of plenaries in the morning as well as parallel breakout sessions at other times during the day. And please remember there's a group photo at 5:30 by the Slack fountain, and bring your t-shirt if you want to. There's also a reception tomorrow evening. And we have a number of other sessions, including breakouts and unconference and poster sessions and research bites. So it's a full schedule. Please look at the agenda for more information. All right, so I'm going to hand this off to our first speaker, and we'll go from there.
Okay. Okay. Morning. Good morning. I'm Lee Jung-kang, and I'm observing specialist postdoc from Slack. And I think this is the first time this part, the name of this part is not anymore the telescope site. Now, as we start operation and the survey, now this part should be the Rubin Summit operation. So I'm gonna talk about this. 1 second. Here you go. Okay, so Rubin Summit operation team is people who has a responsibility to ensure that the scheduler-driven data for the 10-year LSCC survey are efficiently obtained, including the direct on sky observation and calibration data and the technical data that captures the state of the observatory at the time of observation. So we have an observatory facility, the telescope and other facility at the summit. So this is our summit facility at Cerro Patron, which is 2 hours away from the La Serena, where our base facility located. So in base facility, we have a data access center, and also we are supporting the operation from there. At the observatory summit facility, we have a Simony Summit telescope, And then also we have auxiliary telescope. And together with on the calibration hill, on the bottom picture, there's another hill in front of our Simony survey telescope. There's together with the auxiliary telescope, there is DIM, the differential image motion monitor, which is for the seeing measurement. And also we have DREAM, the Dutch Rubin enhanced atmospheric monitoring camera there, which is for the monitoring for the old sky. And the telescope itself body, it's a telescope mount assembly, which is very compact and then very steep, so we can move very fast to the next target. And this facility also have a dome with a light windscreen, and then it's a crawling to follow the TMA during the night operation. And on telescope, we have a primary and tertiary meter together, and then also we have a secondary meter system there, together with M2 and the camera hexapod and rotator there. I'm gonna show you again later. And also our observatory is controlled by software. So lowest level controllable entity of the Rubin control system are the individual, the commandable SAL component or CSC. Here the SAL is the service abstract layer, which is the core communication middleware that connect all the hardware and software subsystem, which is controlling the telescope, not only telescope, but all the facilities at observatories. And here the CSC are responsible for managing the incoming traffic of the data, and also it takes appropriate action. So this is open the controlling of the hardware systems like our meter, and then telescope body, the telescope mount, the TMA, and etc. Also, it's a kind of a pure software. And scheduler with the CSC and algorithm is the brain of the observatory. Maybe it can be covered later in this session. So I'm gonna skip that part. And the engineering, the facility database, the so-called, it's hard to see, sorry, EFD, which record all the interaction between the component that occurred over the middleware. And it's during the night and daytime even, the observers and the engineers or mechanics, we are all using this one for the actively monitoring telemetry from all the system, and then further do the further analysis for validation and verification the system's performance. And this is Rubin's Simony survey telescope has the unique 3-meter optical design, accommodate with the 3-degree field of the view, fitting the largest camera in the world. So the primary meter is 8.4 meter, and then together with the 5-meter tertiary meter in the center. And then center of our M1M3 system, there's a laser tracker, which is for alignment. And also we have an M2 with the 3.4 meter. And as you can see in the maybe next slide, that the optical arrangement system is very compact. It's the F ratio is about 1.23. So it's very shorter than the other similar size of the telescope. And the active optics system, the AOS, maintain our image quality across the wide field of the view by continuously adjusting the shape and then position of the M2 and the camera relative to the M1M3. So it's correcting distortion from the gravity or temperature shift and other perturbations. And real-time control also is done by the wave front sensor, which is on the focal plane of the edge of the camera. Camera. And lookup table is also the first order correction for the predictable pattern for AOS system. And we have also calibration system. So inside the dome, we have in-dome calibration, including the calibration screen, which is about 10 meter. And also we have a collimated beam projector, CBP, which deliver a collimated beam directly into the primary meter, which is near the calibration screen. And also we have Oxtel, which is for the atmospheric transmission. So now also the system integration and commissioning, the so-called SITCOM is not there anymore. It's into now the Rubin Summit operation too. So it's into the RSO. So this is our telescope, and this is the TMA body. And then there's an M1M3 on the M1M3 cell. And you can see it's a little hard to see, but there's a camera on the top end, and then with the rotator, camera rotator, and then the camera hexapod. Also, M2 has a hexapod, and the white screen is our calibration screen. So it's rotated with the dome. And not last but not least, so this is our dome, which is actually still kind of ongoing for the construction or integration. So this, okay, sounds great. So this is the left picture is for showing the dome aperture shutter is open right before the start in the night observation. So it's during the twilight. So we are starting venting, I think. And then second picture, you can see the light wind screen is installed. So so far, 4 light wind screens are installed, and then another 2 gonna be installed soon. I don't know. Yeah, it's installed in the future. And the third one, there's some kind of looks like there's some window, which is the dome louver, which those dome louver is mostly for we open before the starting the night observation to make in dome there's the thermal equalization happen to prevent the dome seam. So that's it. That's important for the observing team and observers. It's important to open that one in the proper time to vent the air inside the dome. So this is a kind of an update from the last year to now. Okay, I think I'm done. So, yeah.
Hello, everyone. I'm your next speaker. I'm Kevin Fanning. I am one of the camera scientists based in Chile. I see people moving. You can hear me, correct? Okay. Next slide, please. This is in front of you an exploded view of the LSST camera, which is the largest digital camera in the world and delivers us an impressive image quality across a 10 square degree field of view, more or less. This is a quick overview of it. Some key highlights here to keep time are that we have 2 mechanical systems, a shutter in the front, sort of down in the lower left, and then a filter exchange system to change between our 6 optical filters that we're taking the survey in, U, G, R, I, Z, and Y. The filter exchange system only holds 5 of the 6 filters, and we have a loading process to change between the 6th one. Another part of the camera that's important to know is that we have 3 temperature zones, more or less. The cryo refrigeration zone, which cools our focal plane, the detectors, down to about -101 Celsius. We have a cold zone behind that inside the cryostat as well, kept to a vacuum for insulation, down to -40 C, which is thermally connected to the readout electronics. Outside of that, we have more or less ambient temperature, auxiliary electronics, power supplies, and such, and then the air that blows, keeping the optics nice and dry and thermalized. Next slide, please. One of the best ways to get a sense of this camera is to look at these beautiful pictures from construction. Here we can see the different pieces going together, and importantly, we see the filter loader in the upper right, which is how we take filters in and out of the camera. I encourage you to go back to these slides later on and check out these videos. There's one of the shutter opening and one of the filter being exchanged inside the camera. These help you understand the mechanics of these systems. Next slide, please. Oh, the videos will play. But okay. When you're looking at Rubin data, it's sort of important to know how our focal plane is structured. We have 205 CCDs, 189 of them are science sensors. The other remaining are for guiding and focusing of the instrument. These are organized into 3 detector groupings where they share readout electronics. And then 3 of these readout electronics will go into a science raft, as we see in the diagram here. Each of these detectors are individually named and labeled, so when you're looking over data, you can go through and pick out certain detectors or just look at full frame images as well. I encourage you to review the detector layout and numbering tech note that is linked in this slide at a later time. Next slide, please. As for camera operations, we are in operations and largely continuing. We have a few pictures here of some of the key things we're doing on a day-to-day cycle. We have a lot of maintenance work on our cryocompressors to keep them running and keeping the system cool. We also have our operators in the control room every night monitoring the camera telemetry, making sure it's stable, at least when there's not a storm on the summit. In the middle, we see the team performing a filter swap on the camera. This is an operation we do more or less once every other week to swap in and out the U and Y filter, depending on the moon phase. And then to the far right, we see the camera in total installed on the telescope between the M2 mirror. Next slide, please. To give a brief status on the operations, barring the storm, the camera is more or less operating nominally. We have one CCD that is not powered on, and this is as we reported last year, so no change on this front. And it's expected to remain this way for the whole survey. This is a pretty good survival rate for CCD cameras on Sky in reality, so we're pretty happy about that. The cryo refrigeration system was known to have an ambient temperature sensitivity last winter. I'm happy to report now that that's resolved and we seem to be able to survive at lower temperatures again through the winter. The camera currently is operating at a higher vacuum pressure than normal, which is an ongoing investigation by the team. And one of our 2 filter loaders is offline. So there's always work keeping us busy to keep the system running at tip-top performance. Related to that, there's a lot of engineering work that keeps us busy as well on the camera team. Cryocompressor module upgrades are in progress. We're working on our shutter extraction rail system for when we have to replace the shutter when it reaches its lifetime. The filter exchange system has maintenance as well as a mechanical system, and we're doing a lot of cross-training in the team. You can see a picture of that from just the other week where we had engineer and myself inside the filter carousel demonstrator to train on the system. There's a lot of software improvements always underway. Alarm accessibility and automation are 2 of the big topics on this front. I'm happy to talk more about that offline in Slack. And as always, we are increasing our understanding of the focal plane and detectors on the camera. If you happen to stumble across anything weird in images as you're looking through the data, please let us know. We've probably found it, but there's a chance we haven't, and we'll need to identify it and understand it. Next slide, please. This will be the last slide for me, but This is a demonstration of why we think we'll come online just fine after the storm. We did a lot of prep work beforehand, covering up the camera to make sure it's safe in case of any water ingress in the dome, however unlikely as that is. We also have the pump cart connected, ready to turn the camera back on and cool it down once we're back in and able to access the summit. Thank you, and I believe the next speaker is Peter.
Hi, everybody. I'm Peter Yoakum here for the survey strategy team, which is also Lynn Jones and Eric Nielsen. So kind of going over the basic jargon of how we talk about the survey strategy. We have our baseline survey. Here's a projection of the sky with the South Pole at the center, so a little different projection than usual. But we've designed the survey. What we call the main survey is usually wide, fast, deep. And so that's the footprint that covers 18,000 square degrees. And we try to get 800 visits over all filters over the 10 years. And that works out to an average cadence of about once every 3 days. And usually we're trying to take those observations paired. So with we take an observation, switch filter, take a second one about 30 minutes later so that we get color information for all those alerts that are coming out. So the wide, fast, deep is that light baby blue is the main part of wide, fast, deep. And then we've also got in green the Magellanic Clouds and part of the galactic plane are also in that kind of 800 visits by the end of the survey. We've got the deep drilling fields marked in red. We'll talk about those a little bit more. So those are targeted deeper observations, and then mini surveys to kind of fill in some other areas. We've got the dusty plain, the South Celestial Pole, and the North Ecliptic Spur. So those are the mini surveys that are also included in the strategy. And we have surveystrategy.lsst.io if you want more on strategy. So here's kind of the jargon we use. We often talk about OpSim runs. OpSim is short for Operations Simulator. It's been around forever, but basically we simulate the operations of the telescope, including weather, dome motions, all that kind of stuff to generate a list of what we think 10 years of observations could look like. So it's basically an observing log of nearly 2 million observations. So if you want to say how well you observed this part in the sky, you can look at our simulations and say, okay, that's how we did. We have MAF, the Metrics Operations Framework, and so that's for analyzing the outputs of OpSim so that we can look at individual science cases and say, how well can we do different sciences given our current survey strategy? And so the plot up there shows how well you can measure proper motions of a given star given a simulated survey. And so you see the deep drilling fields we can measure proper motions really well there, and we can measure them pretty well in the wide, fast, deep. And then those mini surveys where we're doing less observations, it's less well. So if you have a science case, you want to say, how well can I do my science? You should definitely plug into this. We have the SCOC, the Survey Cadence Optimization Committee. If you want to say we should radically change our survey strategy, those are the people you should talk to. We have the FBS, or Feature-Based Scheduler. This is the software implementation of the strategy. It's what I call full self-driving mode for the telescope. They turn this on and it makes every decision during the night of where to point the telescope. So that's taking the SCOC's English words and translating it into code. And then we have SchedView, which is another visual package for looking at a lot of times the observations that are coming out of the telescope on an individual night, so we can see how well we've done. The survey strategy, just to run through quickly, this feature-based scheduler, it's basically a dynamic decision tree for making real-time decisions. And it goes kind of top to bottom. Here's the priorities that the telescope steps through. Our first priority is any target of opportunity, so gravitational wave follow-ups. And in our simulations, this is only about 4% of the total exposure time. So we do have some time carved out for TOOs. The DDFs are next up if there's a DDF up that we want to observe, and those take about 7 or 8% of the total time. Jelko talked about in the previous session, image templates. These just run in the first year where we hammer the sky along the meridian really fast to try to make sure we get enough templates. We figured we had to put this in because there's not enough dark time to get U and G completely covered the sky if we don't put this extra layer in. Then we have a small section for doing kind of 3 to 6 hour time scales. Every 4 or 5 nights, we'll start tipping the telescope far over, get an area in 2 filters, and then wait a couple hours for it to rise up and get it again. Because if we didn't do this Rubin would never sample that 3 to 6 hour time window. We wouldn't get sampling there. So that's in there. And then the main workhorse is our large area pairs, almost 70% of the survey. And that's what I've got plotted here, just on sky and then in alt-as space, what that looks like after 10 years. So that's the real workhorse. That's where we're just observing a giant blob, usually near the meridian, swapping filters, repeating the observations, and moving on and on and on. 1% of the time is for interior Earth solar system. So every now and then at twilight, we tip the telescope way over and point towards the sun as it's rising or setting, so that we can try to get solar system objects which are interior to Earth's orbit. And then finally, the greedy survey, which is if we've run out of time and just can't think of anything else to do, we'll just point around at what we're near and fill in time. Basically, every other observatory, that would be what would be called overhead, where you would be waiting for a scheduled something to start or end. So we don't have overhead. We just observe array and use that 7% of time. All right. Another thing to note is rolling cadence. I said, typically we're observing a spot on the sky about every 3 days. People want to go sometimes faster than that. And so we've decided to do rolling cadence, where we'll do a higher cadence in some part of the sky, and then the next year go much lower cadence and boost the cadence on other parts. So year 1, we do just uniformity because we want to cover the sky, get templates. But then year 2, you can see we've got regions that have been emphasized a lot. They've gotten much higher cadence, and other parts of the sky have fallen behind. And then we give those other parts higher cadence to catch up. And so we're currently debating which years we should target to get back to uniformity, and when exactly to put these rolling seasons in. But this is how we're going to get higher cadences than we would typically get. A slide on the deep drilling fields. There's a bunch of depths. I don't know why anyone put that on the slide, but over here you can see we've got each of the deep drilling fields. I think this is for the first year. And so most of the time we do deep observations, but the top there is Cosmos, and we're calling that an ultra deep season. So for Cosmos, and each DDF will get an ultra deep season eventually. Cosmos, we're doing 2 ultra deep seasons back to back to start, so that we can co-add Cosmos and see if there are any systematic issues, make sure we can do co-ads on super deep things. And yeah, so that's, Cosmos is going really deep really fast. Here's the flow chart of how everything works. Basically the scheduler team, we put out our simulations, we release them to the community. The community tells us how their science does. We get strategy feedback that goes to the Survey Cadence Optimization Committee. They ask for new simulations, for new strategies, and it goes around and around until we finally converge and send the code to the summit, and it drives the telescope. So, most people in here are astronomical community. So if you would like to change how we point the telescope, please talk to the Survey Cadence Optimization Committee, or you can talk to me and I'll double check with them, but we can just plug it right in and change how we point the telescope if it's minor. But if it's a big change, you have to talk to them. We have to get approval. And if you want to, discuss how well are we going to do your science after 10 years, please talk to me. We will make some new math metrics so that as we change the survey strategy, we want to make sure we don't destroy anyone's science. So it's been really key in shaping the strategy, getting those metrics from the community. Okay, thanks. Next up is Alex to talk about data management.
Hello, everyone. I'm Alex. I'm a postdoc here at Slack. I'm also part of the, how do you change? Oh, I'm also part of the LSST data management team. So we're the team of scientists that are responsible for taking all the raw data from the telescope and producing all of the software, services, and systems to deliver catalogs and and images to you all. So we're structured in kind of 3 parts. We have the infrastructure part. This is all the computing and storage and networking hardware that most of it is here at Slack, but also at UK data facilities and in France. We also supply the middleware. This is all the tools that you use to go and retrieve the data. There's a lot of data that is going to be coming out of Rubin. And so we've built a lot of very helpful tools for you to get that and process it. And then we also build all of the pipelines that take those raw images and produce the catalog data products. Right now, the biggest thing we're focusing on is releasing Data Preview 2, which is all the data from commissioning and pre-survey operations using LSST CAM. So this slide kind of goes through what is the actual process once we actually take an image and where you can get all of the data. So once a raw image is taken, within 60 seconds, those raw images are processed compared to templates, which are the high quality co-added images of the night sky. And we compare and look for all the differences. And we find all the things that change and label them as difference imaging sources or DIA sources. Those ultimately then go to alert brokers. There are 6 alert brokers that you can use to look at those alerts. Within 24 hours, these will have the prompt products database. This will include DIA data products as well as early versions of processed images. And then on annual timescales, we'll have data releases. This will include full DIA objects, co-added images, and catalogs for all the data taken to date. We'll also then take all of the DIA sources and associate them to single DIA objects. You'll be able to get all of this data through the Rubin Science platform, which will be talked about next. That's the RSP. So to give you an idea of what we're talking about when we say data previews, so this is all of our data releases and data previews are governed by our early science program. This includes, so far we've had data preview 0. This is all simulated data, and we've taken universe simulations and compiled them into and produced realistic data releases based on them. That's available now. We have data preview 1. This is based on LSST ComCam data. It was released back in June 2025. ComCam is like a smaller version of the big camera. It only has 9 CCDs on it instead of the full 205. That data is out and available now. Alerts have been available since early 2026, and you can get those from alert brokers. The prompt products database will be released probably late 2026. We are working with data services to get that to you as soon as we can. And then currently we have data preview 2, which is going to be released on a rolling basis. So you'll hear something called early DP2 that is released, that will happen today. That will include coads and object catalog level data products. And then the full DP2 will be released around October, December, where we'll add single visit level images, or what we call processed visit images, or PVIs. And then we'll look ahead to data release 1. This will be the first full year of LSST data. That will probably be around early 2028. It'll take about a year to take the data and then a year to process all of that data. So if you look at what is going to be in DP2 and what are the products that are going to be available. So DP2 includes all data taken between 20th of April 2025, which is not long after our first photon, to 21st of September 2025. Then we had a down period, and then it will include more data from October 20th to early 2026. It was all processed here at the US data facility at SLAC with some pilot processing at the French data facility IN2P3. So early DP2 will include the COAD region, which is that region along the ecliptic and the deep fields. And then the full DP2, which is the full area you'll see there, will be included in October, December. This phase delivery is determined by the readiness of the US Data Access Center. So here's some helpful links if you want to get started with LSST software to access this data. You can access it through the Rubin Science platform, where all these tools are installed for you. We have 2 links here. They're pretty easy to remember links. Pretty much everything is something.lsst.io. You can get the documentation for Data Preview 1 and Data Preview 2. We also have the corresponding papers for those releases. RTN 115 has a draft, first draft that is available today. We also have documentation for all the pipelines. That's all the software that we use to process all the images. That'll be pipelines.lsst.io. We also have a number of technical documentations, like little tech notes, that'll be available at lsst.io. The Rubin Science Platform, which we talked about next, is there. We also have lists and tables of all the data products and their definitions, what they're called in code, so how you would actually query it, and what it actually is. That's right there in the DPDD, the Data Products Definitions database. And we have some also recorded presentations. So if you're interested in that, you can get information there too. And we have updates from the science pipeline team, which will focus on DP2 on Thursday at 1:30 in this room. So thank you.
Okay. Hello, I'm Gloria Fonseca Alvarez. I am a postdoc at NORLab in Tucson. I am a member of the community science team, which I'm not sure if you know, but one of our roles is to try to show the community how to access data using the Rubin Science platform. As you might have heard, you will not be able to download the entire LSST dataset due to its size. So the Rubin Science platform is a web-based set of applications and services that will allow scientists to access and analyze LSST data in a way that is next to the data. It has three different aspects, what we call aspects, the portal aspect, the notebook aspect, and the API aspect. And I'm going to talk a little bit about those. So to actually go to the Rubin Science platform, you have to go to data.lsst.cloud. And this is what it will look like. If you go right now, you will not be able to access it since it's currently unavailable to prepare for the release of the early DP2. But if you're interested in participating, we'll have a lot of different hands-on sessions this week. So, and you will need an account. If you're interested in accessing Rubin data as soon as this week, you can go to lsst/RSP signup. You do need data rights, but you can see in that link what who all has data rights. But once you have your account, you'll be able to access the data using the Rubin Science platform. What do you get with your RSP account? Like I said, this is how you'll be able to access all of the data from the Rubin Observatory. If specifically in the notebook aspect, you get some personal storage of 40 gigabytes. You have some compute power of 4 CPU and 32 gig and up to 32 gigs of RAM. You do have the ability to make user managed groups. So if you want to share files with your research group, or for example, we have people who do this for like a workshop, they'll create a group where they can put all of the different, things that they're doing. But if you're interested in seeing what will be available in the future, you can go to rsp.lsst.io, and there is a roadmap for the RSP. So I'm going to talk a little bit about the different aspects of the Rubin Science platform. So the portal aspect is a graphical interface that allows you to explore data. So this is great if you have no programming experience. So like if you're a student just getting started, you can go and just click around and you can access the data right away. Or if you are looking to just like quickly look at an image, for example. All of the services are provided in IVOA standards. That's the International Virtual Observatory Alliance. And you'll see a couple of terms often this week, probably. TAP, which is the Table Access Protocol. That is how you typically query the database. And then you have Simple Image Access, the SIA service, I think SIA. But yeah, like I said, you can use the portal to browse data sets, look at the catalog schema. So our tables have a lot of different columns. So if you want to just quickly see, what like what columns are in a particular table, you can do that through the portal, and you can retrieve and display data, and you can create interactive plots. So the image here shows you what results look like if you query something through the portal. It shows you, like, for example, this shows the HIPS map, a table with the data, and then a graph that you can interact with. Now, the notebook aspect allows you to actually programmatically access the data. So this would be like your programming. It's a Jupyter Lab platform. It comes with the LSST pipelines already installed. And like I mentioned, you get 40 gigs of storage for CPU and 32 gigs of RAM. You can, like I said, share files with different groups. You can install your own packages, like you can use pip. You can execute your notebooks. You can also do scripts. And as you can see, there's also access to the terminal. And if you want to learn how to manage your groups, there's a link right there. Now, the API aspect. API is application programming interface, and that allows you to access, to interact with the Rubin data services and data remotely. So you can use the API to access Rubin data outside of the RSP, or if you want to integrate the access to Rubin in your own software tools that you're building, and you can also use it to access external data sets. Also, sorry if I have not been holding the mic correctly and you haven't been able to hear me at all. But this just shows you an example of accessing Rubin data with an API with Topcat. So you can, if you're familiar with that, this is what that would look like. All of the Rubin Science Platform documentation lives in rsp.lsst.io. And as you can see here, you can see where to sign up for an account. There's also user guides for all the different aspects. This is particularly useful for the API since you can see exactly how to actually access the data that way. There's also avenues for support. So if you have any issues with the Rubin Science Platform or the data, or if you want to just chat to other scientists about Rubin Science, you can go to the Rubin Community Forum that lives at community.lsst.org. And we have a support category where if you post in the support category, you will get a response from Rubin staff. But yeah, and also later this afternoon, myself and Yumi will be hosting how to get started with the Rubin Science Platform. It's one of the afternoon sessions. So if you want to learn more about how to actually access data, please come to the session. And next is Kristen.
Hello, everyone. Let me make sure I know how to advance my slides. Hi, my name is Kristen Metzger, and my home base is with the Education and Public Outreach team, but I'm here to talk to you today about communications. I sort of sit in two spaces. One is with EPO, and Claire will be talking about that next. And then the other is with the communications group that does external communications for Rubin. So, nope. The big one. All right. The first thing I want to talk about today is our name. How many of you in this room would identify as very new to Rubin? Okay, so that's great. I'm glad you're here, and I want to talk to you a little bit about how we like to use the Rubin Observatory name. So there are guidelines for name usage. I'm going to be giving you guys a lot of resources today. Rather than throwing jargon at you and explaining things that you'll probably forget, I'm going to try to direct you to places where you'll be able to find things that will help you in the future. So on rubinobservatory.org, our main public-facing website, there are guidelines for how to use the Rubin name if you're writing papers or basically anything that you need to use the name for. Our full name is NSF DOE Vera C. Rubin Observatory. The first time you use it, but you can say Rubin Observatory or Rubin after that. We'll conduct the Legacy Survey of Space and Time, which is LSST, using the Simone Survey Telescope and the LSST camera. So all of these different pieces have a history and a reason they're named that way. which I'm happy to share with you on the side. But if you go to that link up at the top with the name guidelines, you'll be able to kind of get the information you need as you're writing things about the observatory. The most important thing, though, is that we really, really encourage people not to use the acronym VRO. As much as I know you love acronyms, and it's nice and short and sweet, we really want to make sure that we're honoring Vera Rubin with our name. It's really important to us. So please spread the word, let your friends know, just say no to VRO. That would be great. We appreciate your help with that. So Gloria just did a really nice job of showing you where the Rubin Community Forum is. I wanted to just direct your attention to a few comms resources that are more kind of for the science community as opposed to external communications. On that same observatory, Rubin Observatory website, you'll find a for scientists section. If you haven't already seen that, the community science team does an amazing job providing so many resources for you. So you can always start there, find those resources. That'll take you to the community forum, which Gloria was just talking about. And then, of course, there's the Discovery Alliance Slack space, which there's a link to that there. If you're not on that space and you want assistance getting access to it, you can speak to me or you can speak to a member of the community science team. But essentially, it is a space that's open to anybody who is using Rubin data or interested in Rubin to talk and to get resources to. Okay, so external communications. This is things like press releases, public announcements, media relations, that kind of thing. You may have heard that early DP2 is happening today, and that's very important to everyone. That's happening no matter what, but we really like to let the public know what we're doing when exciting things are happening as well. So there will be a more public announcement about that as well. So the group that works on these types of external press releases, announcements, media relations, that kind of thing, is a distributed group. So it's not just people who are Rubin staff. We've got representation from Noir Lab, from Slack, from Aura, and then from Rubin EPO. I participate on that group, and they're the ones that you want to get in touch with if you have something that you think would make a great press release or a great public announcement, or if you have questions about any of the news articles you've seen. You might have seen in the plenary slides this morning, there were some sort of snapshots of really cool press that Rubin has gotten. There's a lot of work that goes on behind the scenes to make sure those announcements and those press releases get out. I won't bore you with the details of that, but I'm happy to chat with you about it, as are other people on the comms group. The most important thing to know here is these two emails, comms@noirlab.edu and media@slack.stanford.edu. Those are the emails that you'll want to send things to if you have questions, if you have an idea for a press release, if you have any media interactions. Those are the two emails you need to know. I wanted to make sure that you have a face to attach to those emails. And so Josie is here in the room. That's Josie. And I put Manuel's name on the Slack one because he was the one in charge of it when I left for vacation. He's back there in the back of the room. He is certainly going to still be participating on that comms group. But Hillary Smith is here with us. She is brand new to that position and will be helping with press releases and stuff too. So when you send emails to these faceless emails, these are the people who will probably be responding to you, or backups if they're not there. But we want to make sure that we're very responsive and helping you out with anything you need. If you lose those emails and you forget everything else, go back to rubinobservatory.org. There's a media page and there are media resources. Those emails are right at the top of that page, or just Slack, and I'll tell you. Yeah, that's it for that one. So we really want to help you share your science as you're going forward, as you're, making great progress and doing great science. We are the ones who will help communicate that outward. It might be with a press release. It might be with a web announcement. It might just be on social media. It depends on a lot of factors. So get in touch with us, ask us. There are guidelines for how to do that I won't go into right now, but I've provided both this link and this QR code for you we've got a flyer that explains how you go about getting in touch with us and what you need to do to help us help you get your science out into the world. We're very excited to do that. You may be contacted by the media. That happens a lot. People who work for Slack or Noir Lab, Aura, are required to submit media inquiries for approval by our funding agencies. That's not the case with every organization on Earth. It is the case with Rubin. So if you are contacted by the media, if you work for Slack or Noir Lab, you need to do this. If not, we still encourage you to do this. Contact those 2 emails. Let us know. You can just forward the original media request. We will go through the process of getting those approved by the agencies. They want to make sure that people who are speaking with the media have media training, kind of know what to expect, and do a really good job representing Rubin. So again, if you work for Slack or Noir Lab, this is required. If you are part of the broader science community, it's still very encouraged. And that way we know what's going on. We know which media are planning to do stories. We can keep an eye out for it. We can help amplify them, that kind of thing. So we have a list of things that we'd like you to include if you do submit media inquiries. But again, you can just sort of forward the whole thing and someone will get back to you very quickly. We push those through as quickly as we can. And then there's the opportunity for media training. Thank you. It's really important if you are going to engage with media that you feel comfortable and confident and know which topics that you might not want to talk about, but that you can sort of push to other representatives in Rubin. We have some media training resources. We pulled these together when we were doing the First Look campaign. And they are things that I think are really useful. I try not to talk to the media much, but I think they're really useful and that anyone could benefit from them when you're talking to really any member of the public. But go to that link to find those media training resources and then watch for upcoming opportunities. We're hoping to provide some more sort of formal media training for people, and we'll announce those types of things on Slack as they're available to the broader community. And if you have questions, I encourage you very much to reach out to the 2 emails that I've provided like 50 times in these slides. They're available from our website on the media page, or always feel free to Slack me, Kristen. I'm happy to help. If I don't know the answer, I kind of love finding out who does. So I'm very open to any questions you have or talking through anything with you. And I will just ask, did I forget anything super critical, Josie, Manuel? Okay, they're here all week. I'm here all week. And Hillary, we're all here to help you. So thanks.
Hello, everybody. My name is Claire Higgs, and I am the astronomer on Rubin's Education and Public Outreach team. So I want to give you a little rundown of what we do at EPO. Oh, no. There we go. Okay, so a little overview of EPO. So kind of in contrast to the communication stuff, this is our team works to connect directly with the public. And this is our mission statement. We're really all about innovative, high impact, and data-driven experiences that are friendly and welcoming and accessible to the public. And so we really serve non-specialist audiences. The idea is to be welcome to everyone regardless of their background. I think it's really helpful to share these resources with all of you, because you might be doing outreach, you might be trying to explain what you do to a family member, or you might just be interested. And so hopefully there's something in here that will be of use and interest to you. This is the EPO team. Pretty much all of us are here this week. There's a bunch of us in the room. I don't know if EPO people want to wave for a second. Some over there, some over there. So it's a great team. And if you want to chat with us at any point this week, we'd love to do that. So we do a lot of things. Here's a little bit of a summary of some of the resources we provide. We do a lot of things that are on the website that are web-based. We look after that website. We make a lot of visuals and graphics, like the one that is actually playing. And we do social media. We have a Rubin Basic series, which compiles resources about a specific topic or science or technology. And we create lots of fun and interesting things. You can find pretty much everything on the website. There is also this resource portal, ls.st/resources, which has links to many of these things as well. I'd like to point out our introduction to Rubin outreach slide deck. So this is for anyone who wants to explain Rubin to a general audience. So we have, the slide deck is built, it's fully editable. The idea is take what you want, leave what you don't, edit it as you wish. That's available there. We have it in both English and Spanish. Most of our resources we try and provide in both languages. We update this every once in a while, but it's there and it's for you to use as you wish. A big part of our program, of course, is the E of EPO education. And so we have this formal education investigations. These are investigations designed around a topic for high school through introduction to astronomy first year universities. They are web-based, interactive, currently don't use Rubin data, but will use Rubin data, and are very interactive. The list on the far side is the investigations that we've released, and they're widely used and a really important pillar of our program. Another thing we are doing is creating interactive ways to share Rubin data and visuals. And so here's a kind of 3 examples that we have. We have Sky Viewer and Orbit Viewer. These are sister applications. Sky Viewer is an all sky image viewer. Orbit Viewer is the solar system sibling of it. And our new resource that we released this year is the Rubin Dash, which is showing a little bit more of kind of what's happening with the data in the summit. And so these are ways that we try to provide windows for the public to see what's going on, because of course accessing that data is not only technologically feasible but also complicated, and so these are kind of the welcoming windows to see what's going on. One final thing I want to mention here is citizen science. And so, of course, we want the general public to be part of the discovery process that will come out of LSST. And so we have some projects that are launched. We have some more coming. But I want to point out that the way our citizen science works is we try to support both the public to enjoy these projects and have a great time, but also the science communities who are wanting to run these projects. So we have resources available, like a formal collaboration with the Zooniverse, a pipeline for easily getting data from the Rubin Science Platform to the Zooniverse and back again, and storing your data and things like that as well. So this is another part of our program. So I threw a lot of things at you here, but if you want to learn a little bit more about what we're doing at EPO, we have these lunch sessions. I really encourage you to come. We would love to chat and discuss. These are over the kind of last part of lunch hour on Tuesday, Wednesday, and Thursday, and really there for absolutely everyone. If you want to engage with EPO in other ways, of course, there's the website, there's the resources portal, come talk to us. But I want to also point out there's the EPO Slack channel that's on the Discovery Alliance chat. If you ever have a question, or, hey, do you have a graphic that shows this, or what resources do you have, or can I use this or something, ping us on there and we're happy to chat, or reach out to us at any other time. So I think that's everything.
I'm sorry, I left my hat in my backpack. Do I push the buttons? Good morning. Welcome. I know some of you, but some of the point of this session is I don't know many of you. Please feel free to come up and introduce yourself this week. My name is Michael Woodvasey. I'm a professor at the University of Pittsburgh. My interests are in supernova cosmology, and I've been doing LSST stuff for a couple of decades. But I'm here today as the chair of the board for the LSST Discovery Alliance. And so this is the outgrowth of what originally was the corporation that was formed to start this entire project. And whole complicated, what's the word, rich history. We now exist today to support the science and the scientists doing this, largely through private philanthropy, to really take the power and the potential of LSST to transform the science that can be done and the way science is done. So to be a little more specific, we want anyone who has a question about the universe, for which LSST is a reasonable vehicle, to have the access and the resources to do that, whether that's software, computation and support, whether that's training, or how do you ask questions of these unimaginably large data sets? How do you even just sort of think about that? How do you go from unimaginably large to, oh, I'm not intimidated. This is just a data set. That's great. We have more data. Here's how to ask that question. And then networks for global collaboration, professional development at all levels, from undergraduates, graduate students, postdocs, teaching faculty how to be better mentors. Sorry, that's a specific session. I'm not trying to take credit, but that general idea of building that through success, because some of the endeavors will come through large groups working all together specifically about a project, see like DESC and supernova cosmology for what I'm thinking about. But a lot of it will come from small groups of people in the context of large supportive communities, where the barrier to get your question answered is not, you didn't happen to know the secret magic incantation to get something done, or you didn't know the developer of a software package or who had done that, but to really build those networks. So we have currently existing programs on those three focus areas. So software and scientific discovery, the Link Frameworks program, largely based at CMU and University of Washington, has an incubators program where people with an idea come and they spend like 3 months thinking specifically and getting software help for that. We have a broad picture related initiative, but a little more, very more specific. Project Dovetail, which is much more about, here's a professional software engineer and what can you do with 20 hours of their time? Or what can they do with 20 hours of their time to learn some cool astronomy and help that through? We sponsor community science events and early science with LSST. People in professional development, we have several different programs, fellowships, postdocs, graduate student education programs, and community stuff. This is going to get much larger, but from expansion partnerships of welcoming institutions that are not traditional big R1 institutions and to the research community to childcare support. The thing that if you've ever been at an institution and a university is actually super difficult to pay for, even though it's not expensive. And so we've had a program for a number of years providing childcare support for people to be able to attend meetings. I want to give an important update. Now, this is a little weird because this intro to Rubin, so you may not have known this at all. And I'll tell this again today. But for the past 3 years, our CEO has been Beth Willman, who was actually a decade ago deputy director for the LSST construction project. And she is stepping down. You, before everyone else, because you're at the Intro to Rubin session, are the first to welcome our new interim CEO for the next year as we look for a long-term CEO, Richard Green. Would you be kind enough to stand up and say hello? I only have 9 minutes for this talk, so I can't cover Richard's CV, but as former director of KIT Peak, of the Large Binocular Telescope of UCURT, interim director for several different large projects, NSF Astronomy Division Director, very rich in experience. Please come talk to him. He would be happy to talk to you. Even if you're like, I don't know anyone, I don't sure, come up and introduce. He is friendly. He would like to know people. This is part of why we're here, to welcome and build this community. So come talk to us this week. Richard's here. I'm here. Jenna is not here, but I wanted to mention these are some names you will see associated. Jenna Sokolowski is our chief scientist. Jenna and I actually wrote a paper together like 20 years ago about recurrent nova. And our director of finance, if you get a grant from us, you'll hear from Elizabeth Hiley, and Amanda Preston works for us on development. And I just wanted to, if you want more information and typing long strings is too hard, there's a QR code here. But really, we are here to help organize these and other institutions who want to help, and private foundations and individuals, to come help you be the best scientists you can be, help us be the best science community we can be, to realize the amazing potential of science with Rubin LSST. Thank you.
Thank you. Okay, so I think it's the end of the session. So we went over many different topics. Go to the next slide. Do you know how to go to the next slide? Oh yes, okay. Yes. From the instrument, the data, and more broadly about the communication, EPO, and data access, and SDDA, many different topics. But there are just a few more things to let you know. First, you can join a science collaboration. As Alex mentioned, there are different science collaborations, but can join and learn more. And then community forum, you can post questions. You can see recent announcements in the forum about the access, so web pages and documents about the early science, technical questions, DB1, and soon we also have DB2 about data tutorials. And also talk to people. You will see many different people, especially 2 slides next. You can just ask them what's their experience, what's their idea about the survey and the data. So first is the user committee. So user committee, basically they're getting the feedback from the community about the data, about the science platform, and they will report in 2 years in the report to the Rubin operation director. So you can talk to those people and talk to them about your ideas. And also the community science team. So Christina and I are both in the community science team, and we have many different people. Basically, our goal is to teach people how to use the Rubin data. We make tutorials and give talks. Yeah, and feel free to talk to us. Okay, and the last thing is there are a couple of sessions will be useful for new Rubin users. First is today afternoon, there's early science for DB2 and products also in this room. And then later, there's a session about data access. Get started with the RSP. So you heard talk from Gloria, also in this room. Then Wednesday, 1:30 p.m., there's another session about DB2, like got started with the early data preview 2. And then Thursday morning, 10:30 a.m. about user committee we just mentioned. So you can learn more about the user committee there. Lunch break every day from noon to 1:30 p.m., but the food is not provided, sorry. And this is a map for the main 3 meeting places, Redwood, Kavli, and Trinity. Okay, I think that's it. Yeah, thank you. Yeah, we actually have time for questions. I didn't see questions on Zoom and the Slack, but if you have any questions for the speakers, just raise a hand. Yeah. Yeah. So yeah. Okay. Maybe we can give another round of applause to our speakers. Thank you.
We do have time for a couple of questions. If folks have something that's burning, we'll be happy to answer. Otherwise, we will all be around all week to talk at coffee breaks and other places. But raise your hand and we have microphones if you have a question. Anything on Zoom? We'll wait just a minute. Okay, I guess we can go to break and have a great week.